your slowing down flux. Slowing down flux is inversely proportional to energy. So as the energy will increase, the slowing down flux phi will decrease. As the energy will decrease, the slowing down flux phi varies inversely. So phi, E increases, phi decreases, E decreases, phi increases. Okay, are you getting it?
Yes, sir.
Yes, okay. So again, you can see that slowing down density is constant. It do not vary. It do not vary because it is constant, and its value is the value of the source density. Okay. Then moderation of neutron in medium with A is greater than 1. So you can see that F2 is equal to S by 1 minus alpha square E0 ln E0 by E, where alpha E0 is smaller than E0. So if E is in between alpha E0 to E0, then it has a value. So F2, you can see here the transition. A sketch for computing F2 while slowing down neutron in a medium A is greater than 1. So you can see that there is a transition from D dash to D. And here you can see Q is equal to C 1 plus alpha by 1 minus alpha ln E, which is nothing but C J. J is average logarithmic energy decrement per collision, which I have discussed earlier. See here, J decreases logarithmically, and today I have discussed it earlier in this class. See here, J versus mass number A. So you can see as mass number increases, A increases, both exact and approximate value for formula, you can have your logarithm, the value of J decreases logarithmically. And you can see also in the expression, J is equal to 1 plus A minus 1 square by 2A, logarithm of A minus 1 by A plus 1. So it decreases logarithmically as shown in figure 6.1. So hence it says that the average logarithmic energy decrement per collision, equation 7.26. The value of Q has to be equal to the source and density S for an infinite pure scattering medium, assuming steady state behavior without absorption. Thus the constant C is equal to S by J, where S is the source energy, and your J is the average logarithmic energy decrement per collision. So the collision density F, you can write S by J. So flux after n collisions with monoenergetic neutron source in a purely scattering infinite medium can be shown as shown in figure 7.3, and it is a fluctuating signal. In the x-axis, you have energy in logarithm scale. In the y-axis, flux of a neutron after n collisions, and it is nothing but the energy. And your total flux or lethargy, which I have discussed earlier in this class, if we plot total flux or lethargy with respect to energy in logarithm scale, you have a trend like this: total flux per unit lethargy with monoenergetic neutron source in a purely scattering infinite medium. So you can see alpha to the power 5 E0, the value of alpha to the power 5 E0 for all nuclide A is greater or equal to 6 is higher than the upper limit of resolved resonance region for uranium-238, which is 20 kilo electron volt, and E0 is the average fission energy of 1 mega electron volt. So there is a transient, you can see, and significantly it is less for lighter moderators. No transiting seen for A is equal to 1, and for A is equal to 2, the flux does not deviate more than 0.2% from the asymptotic value. Further, fission neutrons are emitted with a spectrum of energies, and this spread in the source energy reduces the effect of Placzek transient even further. Okay, so it is a good assumption to use the asymptotic form of neutron flux in the resonance range. Next, we will discuss neutron slowing down with absorption in an infinite medium of moderator and resonant observer. One is NR approximation, then NRIM or WR approximation. Then you have intermittent resonance or IR approximation. So slowing down in an infinite medium with weak absorption is known as Fermi is described by Fermi S theory. And here you can see the Selegnot-Gottesel approximation or SG approximation. You have your a balance equation, and the solution shows the spatial depressions are the resonance more accurately than the NRIM approximation. The additional term in the above in the expression provides improvement to the NRIM results. So SG approximation in an improved treatment of resonance absorption. Then GG approximation. Comparison of Xi and lambda for various moderators. You can have hydrogen, deuterium, beryllium, and carbon, and the Xi value decreases as the mass number increases. For hydrogen, it is 1. For deuterium, it is 0.725, so on and so forth. And the lambda value also decreases as the mass number of the moderator increases. Then you have the Wigner approximation. The value of lambda is approximated by Xi, and which gives the result of NR approximation. Okay, and the lambda is smaller than Xi means the smaller self-shielding in GG approximation compared to Wigner approximation. Then you have some terminal questions and some worked out examples in your material. Then neutron slowing down by inelastic scattering. So you know you might have elastic scattering or inelastic scattering in classical mechanics. So we can discuss now neutron slowing down by inelastic scattering. In inelastic scattering, an incident neutron hits a target nucleus. Incident neutron hits a target nucleus, and is quite similar to that of elastic scattering, except that the total kinetic energy is not conserved in the former. The Q value of the reaction has to be taken into account for the conservation of total energy after the collision. Conservation of linear momentum holds good. Hence, in deriving the kinematic parameters for the inelastic scattering, you can use notations of elastic scattering. So you can solve the expression by using the method I have expressed you today earlier in this class in Unit 5, and let us discuss the physics. You can see the threshold energy E threshold ETH is the minimum value of EL above which the reaction can happen, and thus ETH is equal to A plus 1 by A modulus of Q. It means that for an inelastic scattering event to occur, the neutrons are required to have a laboratory kinetic energy in excess of A plus 1 by A times that of the excited energy level. As A increases, ETH is almost equal to the Q value. Numerically, you can have the first and second excited levels in some nucleides. And as we go from lighter nuclei to heavier nuclei, from increased mass number, carbon, oxygen 16, sodium 23, iron 56, uranium 235, uranium isotope 238, and plutonium isotope 239. You can see the first level and the second level and continuum. The first level for carbon, it is 4812 kilo electron volt. For oxygen 16, it is 6430 kilo electron volt. For sodium 23, it is 459 kilo electron volt. For iron 56, it is 862 kilo electron volt. For uranium 235, it is 0.077 kilo electron volt. For uranium 238, it is 45.09 kilo electron volt. For plutonium 239, it is 7.894 kilo electron volt. And for the second level of carbon, it increases then decreases. For second level, it is 8296 kilo electron volt, and for continuum, it is 7886 kilo electron volt. But in case of oxygen, it increases continuously. For first level, it is 6430 kilo electron volt. Second level, 6516 kilo electron volt. And continuum, 10189 kilo electron volt. Similarly, you can see the trend for other nuclei. Energy spectrum of inelastically scattering neutrons. You can see here in figure 8.1 how inelastic scattering of neutrons takes place. Here is a nucleus which hits the target nucleus X having mass number A. Then it formed a compound nucleus having mass number A plus 1. As the nucleon is absorbed in that nucleus and it becomes unstable. Then a gamma ray is being emitted from this nucleus and also N dash. So what happens? You can see the energy in terms of energy levels in the second part of this graph. So available energy in center of mass system, you can have E, and your inelastic group 2, inelastic group 1, and compound elastic group, and your ground state of target and product nuclei XA. You can see there is a transition from transition to E1, E2, and E0 from continuum. Okay. So you can see discrete energy spectrum of inelastic neutron. In the y-axis, you have scattered neutron. In the x-axis, you have energy of scattered neutron. You have peaks. Those signifies inelastic neutrons and elastic neutrons. And continuous energy spectrum for neutron from inelastic scattering of 10 mega electron volt neutron by uranium-238. So your mean energy loss in an inelastic collision, you have the expression E dash bar is equal to integration 0 to infinite E dash P transition from E to E dash D dash is equal to twice T, capital T. So the inelastic scattering of 10 mega electron volt neutron with uranium-238, your E dash bar is 1.32 mega electron volt. So in other words, you can say the incident neutrons on the average losses 8.68 mega electron volt as a result of single inelastic collision with uranium-238. It is to be noted that average energy loss by elastic scattering is uranium-238, and it is half 1 minus alpha 10 mega electron volt, which is equal to 0.085 mega electron volt. If the scattering were isotropic in the center of mass system, average energy loss is significantly less. Okay. Then we shall discuss differential inelastic cross section. The differential inelastic scattering cross section can be computed using the scattering kernel K as sigma E to E dash is equal to sigma E multiplied by K E to E dash transition. So you have your K is equal to 1 by sigma E summation K sigma E delta E minus E dash E K star minus E dash. So your basic information on inelastic scattering for reactor calculation is available in multi-group cross-section libraries. Okay, the scattering kernel appears as a scattering matrix in this set for various Legendre moments. So then relationship between energy and the cosine of scattering angle in the laboratory and center of mass system. So your mu L is equal to mu C root over of EC dash by EL plus 1 by A plus 1 root over of EL by EL dash. So it is the relationship between scattering cosine in center of mass and laboratory coordinates. So your angular distribution of inelastic neutron. The angular distribution of inelastically scattered neutrons are quite simple over most of the energy range of interest in reactor theory, up to around 10 mega electron volt. These neutrons are emitted isotropically or nearly so in the center of mass system. Above 10 mega electron volt, the angular distribution tends to become forward peaked and exhibits a diffraction pattern similar to that found in elastic scattering at this energy. The forward peak distribution is due to neutrons undergoing direct interaction type of inelastic scattering. Since there are comparatively few electrons with such a large energy in nuclear reactor, it is usually adequate in reactor theory to assume that inelastic scattering is always isotropic in the center of mass system. However, the effect of inelastic scattering anisotropy are accounted in the present reactor calculation with the help of multi-group cross-section libraries. So there are terminal questions and solutions in your material. You can go through these. Okay. And tomorrow we shall discuss the third part of your syllabus. Any doubt? You can also go through this material and ask your doubts in the next class. Okay. Am I audible? Today we have discussed neutrons slowing down by elastic scattering. One, neutrons slowing down by elastic scattering. The second part, slowing down spectrum, and a neutron slowing down by inelastic scattering. Okay. Thank you. If there is no question, so we can have this class tomorrow for the third part of this discussion. Okay. Am I audible? If you have any doubt, you can also ask. Tomorrow we shall discuss neutron transport. Okay. Neutron transport. There we will discuss diffusion equation, form of transport equation, Boltzmann transport equation, and some basic terminology used in those. So do you know diffusion? Go through that. And the transport. How energy and particles are being transported. You have studied it earlier. And we shall discuss this in the light of neutron. Okay. So thank you.
No, sir.
Okay. Thank you.